Okay, this is the beginning of another chapter in high school chemistry, and the chapter is in thermochemistry. It's chapter 17 in your book, and that's on pages starts on page 504 in your textbook, and I believe it goes to pages 539. What I'm going to do in this one is we're going to break it up into smaller sections. The chapter is quite long, and we're going to break it up into several sections. But this is just this video is just the intro into what thermochemistry is, some concepts that you're going to have to understand and be aware of, because we're going to use those concepts elsewhere in the subsequent videos, tutorials, to talk about types of heat and reactions and things like that. Okay, our first thing to do is we need to understand what thermochemistry means, or what does it describe, and what's the definition of it. So I've broken it down into two distinct words out of it. So there's the thermo part, and the definition of that, and for this particular application, is it's associated with heat or thermal energy. So when you say thermo, think anything associated with heat or thermal energy. And chemistry, well, you should have a good understanding of what chemistry is now. We've been doing it for a couple of weeks. And the chemistry is the study of matter and the physical and chemical changes of matter, right? So if you combine the two, you get thermochemistry would be the any heat or thermal energy associated with the physical and chemical changes of matter, right? So that's pretty much the nutshell of it. So it's if you were to do this, it's the heat associated with heat or thermal energy associated with physical and chemical changes of matter. All right, so that's the definition. Okay, so let's move on to talk about some other more specific terms specific to thermochemistry that you may or may not have heard of already. Okay, so we want to talk a little bit about this energy and how it applies to thermochemistry. So energy is just basically the definition is basically the ability to do work, right? And this is work that the scientific work, not the 9 to 5 work that you or your parents may go to. And the SI unit for energy is the joule, and but sometimes you'll see that the English unit is called the calorie, and you'll see that at back of food packages. And like the law of conservation of mass, we have the law of conservation of energy, and that just basically says we cannot create or destroy it, but we can transform it from one type to another, right? So that's just the high-level definition of energy, what the units are, and there's a law of conservation that we can't destroy or create energy, but we sure can take it and transform it from one type to another. Okay, so now that you know that there's, we know what energy is a little bit more about. There's different types of energy, and energy I'm not going to go through the whole list here, but you can look at the whole list here, and there's different types of energy, not just chemical energy. There's heat, electrical, nuclear, mechanical, sound, etc., etc. And what I really want you to understand is that we can change between any type of energy back to another type of energy. So let's look at an example here. We have a chemical energy here, this candle. This is a chemical reaction involving wax, which is a hydrocarbon, plus oxygen, and that gives me CO2 plus H2O. And if you remember, you should automatically recognize this as a combustion reaction. And so we're taking the energy that we get from the chemical reaction, and it's being transformed into heat and light energy, right? The candle gives off heat, and candle also gives off light. And then for any of you here that play the guitar or any type of musical instrument, when you strum back and forth across your guitar, back and forth to make the strings move, you're doing some type of mechanical energy there, and that energy then is transferred into sound, right? When you strum the strings, they go back and forth. That creates a pressure wave. They vibrate, create a pressure wave in the air, and the pressure wave is the sound that you end up hearing. And the last one is the chemical to mechanical energy. And basically this boils down to is a food being turned into mechanical energy. So when you eat food, right, you get energy that allows your body to do something later on in the day. So if, let's say, you have breakfast, and that allows you to operate the rest of the day, moving, running around, studying chemistry, whatever, and that energy is transformed from chemical energy when you digest your food and get all that energy out into mechanical energy. If you don't put any food into your system, eventually you won't be able to do any mechanical energy, right? So hopefully that explains a little bit more about the types of energy, and that the ability to go from one type to another type through some type of process. And then so we'll be using this later on in chemistry to understand that we can use chemical types of energy to do mechanical work later on. Through maybe we'll do a chemistry reaction to generate electricity, or we'll do a chemical reaction to generate a mechanical something, or generate chemical energy to generate sound, light, etc., or even heat. Okay, so not only do we have different types of energy, now we have different kinds of energy within each type. And bottom line here is this is what we're going to call potential and kinetic energy. And potential energy in its most basic definition is just stored energy. And kinetic energy in its most basic definition is the energy of motion, right? And potential energy, again, is just energy that's available for use later on. It's not being used now. And kinetic energy is the energy associated with motion. So something that's happening now with if the material is moving back and forth. Either molecules are moving back and forth, or something else is moving back and forth. So you can talk about, like, the bull's running. That bull has a lot of mechanical energy of motion as he runs through the streets. And then our safe here, everything's locked up, ready to go for potential energy. And the best example of a change, and we can change between the two. We can go between here and here all the time. And the best example of that is, for many of you have probably been on a roller coaster. And you know how the roller coasters usually starts out. You start out either you're getting a car, and then you're taken up to some ungodly height to start with. And then what happens is, as the car is released from the top of the hill, where the car is almost stopped, you have your maximum potential energy there. If you remember, if you've taken physics before, or know anything about from physical science, potential energy, the maximum height that you get on that is all potential energy. So the car's not moving, it's all potential energy. And then as you go down your first drop on the car, you go to the top speed that you get there, that's all kinetic energy. So all that energy is being used, the potential energy is being transformed into kinetic energy as the car moves down the track. And then as the car goes up the next little hill, some of the kinetic energy is then transferred back into potential energy, which allows the car to go back down the hill, etc., etc. And every time you go through a loop, you change from kinetic to potential back to kinetic as you go down further down the thing. So that's your best example of a change between potential and kinetic energy, and we can do that also with the other systems that we've talked about. Okay, so let's look at the energy of chemical reactions. Every chemical reaction involves gaining or losing energy, and we define this as heat gain or loss, right? So let's look at that from a real simple standpoint. When we say that heat is gained, heat gained equals plus heat. The plus sign indicates that it's being gained, so we're adding it. Adding heat. It's just the plus is just a directionality. Directional. Has nothing to do with more than 0, less than 0. It's just a directionality. It just tells you where the heat is going, either into the reaction or out of the reaction. That's all it says. Okay, so now let's look at heat lost. All right, heat lost. So heat lost, and that's going to be equal to a negative heat. Again, the negative does not mean it's less than 0. It's just that means that heat is being released. Again, this is our directionality here. This is our directionality. So heat is being released. It's negative. Heat is being added. It's positive. It has nothing to, again, nothing to do with less than zero heat, more than zero heat. It's just a directionality of which way the heat is going into or out of the reaction. So hopefully that will give you a better understanding of what we mean by heat leaving and heat gaining and absorbing, and heat leaving being released from a reaction. Okay, so here's a new concept that even learned scientists sometimes have a difficult time explaining to a young high school scientist, a young high school chemistry student, and it's this concept of enthalpy. And enthalpy, in its basic definition, is just the heat content of a material or the heat content of a reaction. So that's enthalpy is the heat content, and this is our general equation for enthalpy. And you notice here that there are two terms in it. There's this H products and H reactants, right? And it's the difference of the two that gives me the enthalpy of that particular reaction. And the enthalpy, a delta H, is the symbol for the enthalpy of the reaction. And what do I mean by heat content? Well, think about it this way: heat content of a chemical is basically the energy associated with all its chemical bonds. So let's look at this, for example, CH4, which is methane. That has 4 carbon-hydrogen bonds, and each one of those bonds has a energy associated with each bond. So 4 times the energy of each bond, since there are 4 bonds, is what equal the heat content of methane. And you might ask yourself, so what do you mean by heat content? The methane doesn't have any heat associated with it. All the energy that is stored in its bonds is the available energy for doing work. If you break those bonds, that energy is now available to do work, right? So it's the heat content of the bonds. So in other words, if you could take and use all the energy associated, if you break apart methane into its individual components, carbon and hydrogen, the energy associated with breaking those bonds then could be used to do work elsewhere else, right? If you could do that reaction. And if you could transfer it all into heat, remember energy heat is a form of energy. That's what we mean by heat content. So let's look at it really quickly in the simplest definition. Let me erase some of this stuff here real quick. And let's look at it this way. Okay, so we have our reaction here. And let's look at it from, let's just do a simple reaction real quick. So we have A plus B equals C plus D. And basically what's going on here is, in the first case, we have our reactants, and there's an energy associated with breaking bonds because we need to break bonds first. So we're going to first thing we have to do is break bonds. For this reaction to go, we have to break bonds of A and B, and then there's an energy associated with that. There's an energy to break bonds. And then the next thing we have to do is we need to form C and D, and there's a energy associated, so that's new bonds. Let me put that back. That's new bonds. And there's energy associated with that. Energy with new bonds. And there's an energy associated with that. And so the difference between the two energies is going to tell you whether or not you have to add energy to make the reaction work, or whether you have to, or whether you get energy out when you do the reaction. Let's look at it this way. So let's say that the break bond energy for the first case, so it's case 1. Let's just put this case 1. The break bond energy is greater than the new bond energy. Right. So if we do our reaction up here, the break bond energy is going to be greater than that. So if we do our delta H reaction, delta H equals, and then the break bond energy is going to be greater than that. So delta H will be negative energy. Right, you can see that up there. I could put in some numbers here just to make it easier for you if you want to do the math on your own. Let's say the break bond energy here was 100, and the new bond energy was 50. So if you did that math up there, it would be 50 minus 100, and that would be negative 50. So the energy is negative, which means that we get energy out of the system, so it's exothermic. And remember, negative energy is not energy that's less than zero. It's just a directionality of where the energy is going. The energy is leaving the system, so we can use it to do work elsewhere. And then let's take the next case, is where the break bond energy, again, still say it's let's say it's 100 still, so make that 100, is going to be less than new bond energy, and we'll make that 200, right? And if you do the math up there, the delta H is going to be positive energy, which means we need to add energy to make the reaction work. Otherwise, we can't get the thing to work. There's not enough energy from breaking the bonds available to form new bonds of C and D. And so we need to add energy. So it's an endothermic process. Remember, adding energy, the plus means we just add energy. We're adding energy, and negative means we're getting energy. It has nothing to do with again, nothing to do with the plus and minus energy of being negative, less than zero or more than zero. It's a directionality thing. All energy is going to be, the quantity of energy is going to be positive. It's just a directionality of where it comes from. So hopefully that explains the enthalpy a little bit better, and you can see me if you want a more detailed explanation, or consult online. Okay, so let's talk about we talked a little bit, danced around this a little bit in the last section of the video about enthalpy, but we talked about a new concept of exothermic reactions. And remember what we said about exothermic was exothermic means that the energy is being released, right? So we have exothermic reactions. Energy is released from the reaction, so it exits the reaction. So the EX and exothermic. So those are the two things that help you remember this. And we can write it as energy is a product. So we write the equation like this, where the energy is a product. And that'll be useful later on when we do some stoichiometry of enthalpy. And then remember, we said before that the delta H term is going to be negative, right? And again, negative doesn't mean it's less than zero. It just means that the directionality of it is leaving the reaction. And a result of an exothermic reaction is that it gets hot. Opposite of an exothermic reaction is we have an endothermic reaction. Again, endothermic means we're adding energy, so En and entering the reaction. So the energy is absorbed by the reaction, and we write it as a reactant, right? Because we have to add the energy, so energy is a reactant. So here's that. And our delta H is, remember from our previous little slide a couple of minutes ago, what our delta H is positive. And again, the positive means that it's coming into the reaction, not that it's more than zero. And the result of this, even though we're adding energy, is cool because the energy is being absorbed to do something. And we're not adding energy to change the kinetic energy of the thing. We're adding energy as a potential energy. So that it stays cool. So our last slide on this little tutorial is we're talking about this new concept of heat. Now we've danced around a little bit and we've talked about the enthalpy and exothermic and all the endothermic. Heat is just a general term for the thermal energy. And let's talk about what the chemical symbol is for that. And that would be the letter Q. So Q is going to equal heat. And remember we talked about heat content of a chemical being the enthalpy. And so you could say, well, why aren't we using H? What's the difference between H and Q? Q is just the general heat of a process, right? So if you're heating up water, there's no chemical reaction for heating up the water, but you're adding heat to the system to heat the water. So that energy is heat energy, but it's not heat energy coming from a chemical reaction. So there's a difference in the terms, right? Q is the general term for heat, and delta H is the enthalpy or the heat of a reaction. So there's a little bit difference in terms there. And again, the same thing as before. If Q is equals a positive value, then where heat is being absorbed. And if Q is negative, that heat is being released. Again, I have to reiterate this one more time, that if you see a negative heat, it doesn't mean that the energy is being less than zero. It just means that heat is being released, right? And being able to use for something else as far as doing work. So our concept is Q is going to equal our value or our variable for heat. and Q plus is going to be heat absorbed, and Q minus is going to be heat released.